Alright, we are getting ready to start section 2 of chapter 3 on exponential functions. Now, I would imagine I'm not the only one that when they were bored multiplied by 2 and found powers of 2. 2 times 1, 2 times 2, 2 well, 2 times 1, 1 factor of 2. 2 times 2 times 2, 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 times 2. So 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, and so on. This pattern of numbers, this geometric series of numbers, can be described in this function here, f of x equaling 2 to the x, where x is a positive integer. But what we're going to do is we're going to expand what x is, and we're going to allow x to be any real number, and that's when we get what we call an exponential function. Let b be a constant real number such that, this means such that b is greater than 0 and b does not equal 1. Then, for all, or for every, real number x, a function of the form f of x equals b to the x, this guy right here, is called an exponential function of base b. Now, depending on the book you use, you have different variations of this. Sometimes they'll put a factor of a out in front. But in this case, a is 1. So I have some examples that have exponents, and I thought, well, which ones are exponential functions based on this definition, which ones aren't? Well, this one is. That was the guy I was talking about a minute ago. And so is this guy, because your base, 1/2, is greater than 0, not equal to 1. This one is not, because as you can see, the variable is in the base, not in the exponent. And this one is not based on this definition because our base is -3 and that's not greater than 0. And this one is not. So I'm going to X out this one, I'm going to X out this one, and I'm Xing out this one because b cannot equal 1. 1 to the x is the same thing as just 1, and that's a constant function, that's a horizontal line. So we'll throw him out as well. So these two guys are exponential functions. And as I mentioned before, we're going to allow x to be any real number. The domain is the set of all real numbers. The range, as it turns out, when you take a positive number and you raise it to a power, you get a positive number. So the range will be all positive real numbers. Now, one way to kind of see what's going on is to make a sketch of an exponential function or two, and that's what I'm going to do right over here. I'm going to graph. Now, when I've not graphed something before, it's probably would behoove you to make a t-chart. And I'm going to plug in, hopefully, enough numbers to see what's going on and to see if I develop a pattern here. Now, if I plug -2 in for x, 2 to the -2 is 1 over 2 squared, or 1/4. 2 to the -1 is 1 over 2, or 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. Now, I could keep on going, but I didn't make my scale set so that I could accommodate too many more numbers. But you'll see a pattern. The bigger x gets, the bigger the y value gets, increasing, as the term might be, exponentially. So I'll graph these points. See, -2, 1/4 would be about here. -1, 1/2 would be about here. 0, 1 would be right here. 1, 2 would be right here. You can see it's not a line, it's curving. And 2, 4 would be right about here. And in fact, since I know that as this gets smaller, this is approaching 0, I have an asymptote effect. I have a horizontal asymptote here of the x-axis. And my graph is going to climb and get bigger and bigger and bigger. And that's what the graph is going to be. Notice how my graph from left to right is increasing. Now over here, I create a table of values. -2, -1, 0, 1, and 2. And I'm going to plug these in. Now remember, when you have a fraction to a negative power, that's the same as the reciprocal of the fraction to the positive. So 1/3 to the -2 is the same as 3 squared, which is 9. 1/3 to the -1 is the same as 3 to the +1, which is 3. 1/3 to the 0 is 1, 1/3 to the first is 1/3, and 1/3 to the second is 1/9. Now I'm going to grab these points also. Grab a different color pen here. -2, now I made the scale here on the y, each one of these tick marks is worth 2, where on the x it's only worth 1. So I have -2, positive 9, 2, 4, 6, 8, 10, so right about there. -1, 3, oh, it's off a little bit here, I think I can do better there. 0, 1. 1/3. Now this is going to be pretty close to the x-axis, and this one even closer. I don't have a pen fine enough that I could do that. But do you see how the shape is defined? It's kind of the, almost like a reflection looking shape of this one. It's not increasing from left to right. This one is decreasing. And I don't have a steady hand. I do like paper and graph paper and pencil better. And again, it looks like I put this right smack dab on the axis. It's not going to touch the x-axis. The x-axis is going to serve as as a horizontal asymptote. My graph is just going to get very, very, very close to it, so close that it looks like it's right on the line. So just on these two simple examples, I'm going to make some statements here. If you have an exponential function as defined back here, if b is greater than 1, like this example, here b was 2, f is increasing, which we call exponential growth. You can see from left to right, the y values are getting bigger and bigger and bigger. That's the growth. If b is between 0 and 1, as this example shows, f is decreasing from left to right, dropping downward, and we call this exponential decay. The domains are all real numbers, the range are all positive numbers. The horizontal asymptote is y equals 0, which of course is the x-axis. And 0, 1, notice here and here, 0, 1 and 0, 1 turns out to be the y-intercept of these graphs. Now, what we're going to do next is we're going to do some transformations to these basic graphs so that we can look at other types of functions, other types of exponential functions.